In this video, we're going to go over how to do stoichiometry calculations when gases are involved. So the great news about stoichiometry questions is that you're generally doing the same 4 steps for every single questions. It's just which formulas you use are going to change slightly depending on what you're given. Okay, but going over the 4 steps again, the first step is always to write a balanced chemical equation. Then step 2 is always find the moles of your given substance. So when we're dealing with gases, you might be using your ideal gas law, which is PV is equal to nRT. Okay. Step 3 is always going to be your mole ratio. So the mole ratio is going to convert your moles of your known substance into the moles of your unknown substance, or what you're trying to find. And then step number 4 is give the question what it's asking for. So convert moles of your unknown into the units the question is asking for. Okay. All right, so our first example here, we've got what mass of methane gas, which is CH4, burning would be required to produce 10 liters of water vapor at 15 degrees Celsius and 100 kilopascals. All right, so step 1, let's write out our balanced chemical equation. Now, the word burning, that is our key word to tell us that this is going to be a combustion reaction. So remember, combustion reactions, it's always your fuel plus oxygen gives you your products. So in this case, our fuel is methane. Okay, and another thing with this, now if they told us methane gas, but they didn't give us the formula of it, where you could find that is if you go to your data booklet and then go to page 4 or 5, you could find methane. So these are arranged alphabetically. So let's find methane here. So it's on page 5 right here. So that's how you could find out what the formula is if it's not given to you. Okay, but keep in mind that's only going to really work for mostly for organic compounds. So that's just compounds that are mostly made up of carbon and hydrogen and sometimes oxygen. So we got our fuel, which is a hydrocarbon, reacting with oxygen, which is a gas. Okay, now since our fuel is a hydrocarbon, our products are always going to be for hydrocarbon combustion, carbon dioxide, which is a gas, and water vapor. Okay, and our question already does tell us that water vapor is one of our products because it says that it will produce 10 liters of water vapor. So that tells me that this is a product. Okay. All right, now let's balance this out. So we got 1 carbon going in, 1 carbon coming out. For hydrogens, we've got 4 coming in, and we need to make sure we got 4 coming out. So right now there's only 2. So if I put a 2 coefficient here, well, then 2 times 2, that's going to be 4 hydrogens. And the hydrogens are all taken care of. Okay, so just as a reminder, for hydrocarbon combustion reactions, you always balance it in the order of carbons first, then hydrogens, and you always leave oxygen to the very end. Okay, so speaking of oxygens, we've got 2 coming in, and on the product side, we have 2 here, but we've got 2 sources of oxygens here. So we got 2 from carbon dioxide, and we have 2 times 1, so there's a total of 2 from the water vapors. So we've got 4 oxygens on the product side, so let's make sure that there's 4 on the reactant side by putting a 2. Okay, so 2 times 2, That'll be 4. So 4 oxygens going in and coming out. Everything's balanced. Okay, so that is step 1 done. If it really bothers you to leave these blank, then you can always put a 1 in front of them if that bothers you. All right, now we are on to step 2. Actually, you know what? I'm going to organize some information first. Okay, so it's asking us what mass of methane. So I'm going to go mass is equal to question mark. Now, whenever you're asked for the mass of something, you're going to want to figure out, okay, what is the molar mass for that substance? Okay, so molar mass is equal to, and let's just take a moment to figure out exactly what the molar mass is. So pause the video, take a second to figure it out, and then you can press play once you've figured out the molar mass of methane. All right, just to show you how I'm doing it, so I've created this chart to organize my information. So I've got elements in the first column, then atoms, then molar mass of each of the elements, and then totals. So what we're doing is we're taking the amount of atoms and multiplying it by the molar mass. So for carbon, there's going to be 12.01 grams per mole. And then for hydrogen, since there's 4 of them, times the molar mass of each hydrogen atom, which is 1.01. So that gives us a total of 4.04. Now we're going to add up both of these numbers. So what we're going to get is 16.05 grams per mole for the molar mass for methane. All right. Now it says that we're going to produce 10 liters of water vapor. So I'm going to go over to water vapor and go, okay, my volume is 10. And then they give us a temperature of 15 degrees Celsius. But if you remember from the gases unit, we never use degrees Celsius in our calculations. We always need to use Kelvin. Okay, so to convert from degrees Celsius to Kelvin, we need to add 273.15. Now, if you're curious as to if you had to memorize this number, well, you don't really. So if you go to your Nelson periodic table and go to the second page, down in the right-hand corner here, it gives you this value. Now, this does say to use 273 Kelvin. Don't listen to that. Use 273.15 because the more digits you have in your number, the more accurate your final answer can be. All right, so if we add those two numbers together, that's going to give us 288.15 Kelvin. And then looks like our pressure is 100 kilopascals. Alrighty, so I'm going to have to get rid of this just so that I have enough space to do my calculation here. But now that we have our information organized, we're going to move on to step 2, which is find moles of our given. So the substance we have the most information given for, that's going to be water vapor, so that's where I'm starting here. Now, since I have pressure, volume, and temperature, if you look at your formula sheet, you'll find that this gives us the most information to use the ideal gas law, which is PV is equal to nRT. So looking at our formula sheet here, this is what I'm talking about. So looking at these formulas here, the ideal gas law is right here, and how you can choose what formula to use is, let's just add our unknown down here. Right. So how we choose our formulas is you got to look at what you're given in the question. Okay, so for this section, I'm saying to myself, okay, I've been given volume, temperature, and pressure. I know I need to find moles. The reason why I should be using PV is equal to nRT is because we do have pressure, we have volume, we're trying to figure out what moles is. R is the ideal gas constant, so you always have R, and then temperature we have given to us in the question. Okay, so if you have only one question mark, that's a pretty good sign that that's the formula that you should use. Okay, so if you only have one unknown in the formula. All right, so let's get that started over here. So PV is equal to nRT. So we want to be finding moles. So we got to ask ourselves, okay, what is the ideal gas constant and temperature mathematically doing to moles? And we need to figure out the opposite of it. So these two are multiplying moles. So the opposite of multiplying is dividing. So I'm going to divide by both R and T. So these cancel out. So we get PV divided by RT is equal to N. So that's going to be the formula that we use for step number 2. So let's just flip this formula around. So N is equal to, so our pressure, that was 100 kilopascals. Volume, that was 10 liters. Divided by our ideal gas constant, so that's 8.314. Now if you're like, hey, it's been a minute since we've done the gases unit, I did not remember the ideal gas constant whatsoever, that's no worries. So once again, if you go to your Nelson periodic table sheet, and then if you just, so I'm just in the lower right hand corner of the second page. If you go here, R is a constant that's already given to you. So it's 8.314 kilopascal liters per mole Kelvin. Okay, and then temperature, that was at 288.15. All right, so how the units are going to cancel out, kilopascals on the top and the bottom, so they cancel out. Same with liters, and Kelvin are going to cancel out as well. So let's put this into our calculators. So I'm going to go 100 times by 10 divided by 8.314 times by 288.15. Close the bracket. Okay, so we're getting 0.4174, goes on forever. So remember, the ... just means that I'm not rounding, the number keeps on going, but I don't want to write the entire thing. Okay, that's all that means. I am still using this entire number when I do future calculations. Okay, so that is step number 2 done. Now we're on to step number 3. So I'm going to use a different color to show that this is step number 3. Which is the mole ratio. So actually, before I do this, I'm going to say this is moles of, and since all this information came from water vapor, I can say, okay, this is moles of water vapor. Okay, so now we're doing the mole ratio. And remember, the mole ratio is going to be the coefficient of what you want in the numerator divided by the coefficient of what you're given. So that's why I wanted to write out the identity of the substance, is just to make life easier here. So we're given water and we want methane. And now I just look at my balanced chemical equation. Okay, the coefficient in front of water, that's 2. Coefficient in front of methane, that's 1. Okay, so essentially what we're doing here is we're taking our 0.4174 and just dividing it by 2. Okay, you can go times by 1 divided by 2, but this number divided by 2 will give you the same answer. Okay, so 0.2087 goes on forever. And let's see how much room. Yeah, I do got to write it over here just to save myself some room. So 0.2087 goes on forever moles. Now, if you treat water kind of like a unit, so water is in the numerator and denominator, so they cancel out. So the identity of the substance is methane. So I'm going to write that this is moles of methane. All right, now we are on to step 4. So give the question what it wants. And this question asks us, okay, what is the mass of methane? So we're answering this question here. Now, in order to go from moles to mass, that's going to require this formula, which I'm going to use a different color here just to show it's a different step. Maybe I should draw a line right here. So mass is equal to moles times molar mass. Okay, so we already have moles of methane. We already figured out molar mass, so all we need to do is just plug in the numbers and multiply them. Okay, so moles, that's at 0.2087, goes on forever. Molar mass, that was at 16.05 grams per mole. Okay, units are canceling out, so moles is in the top and the bottom, so they cancel out. All right, now let's do this in our calculator. So we're timesing by 6.05. So we get 3.3497, goes on forever. And that's going to be in grams because grams didn't cancel out. Okay, now we got to take care of sig digs. So it looks like all of our numbers in our question here were given to 3 sig digs, so that's what I need to put this to. So if I'm counting from the far left, 1, 2, 3, there's my cutoff line. So my final answer should be 3.35, and that's going to be grams of methane there. Just as a quick reminder here, if you're wondering why we use the molar mass of methane here, it's because we had the moles of methane here. So what I'm trying to say is the moles of this substance need to match the identity of the substance that you're using for your molar mass. Okay, you can't use the moles of one substance and the molar mass of a different substance. They have to belong to, like moles and molar mass, need to belong to the same substance. Okay, next question. What volume of hydrogen gas at 94 kilopascals and 24.5 degrees Celsius could be collected in the reaction of magnesium with 10 grams of water? Okay, so this reaction of magnesium with water, okay, that tells me that magnesium and water, we're reacting them together, so they have to be our reactants. Okay, another clue here is that we're told, okay, hydrogen gas could be collected. Okay, that can only happen if it's a product. So let's start building our balanced chemical equation. So we've got magnesium, which is a solid at room temperature, with water, which I'm going to write as HOH just to make figuring out the products a little bit easier. Water is going to be a liquid. And since we have an element reacting with a compound, this is going to be a single replacement reaction. So I need to figure out, okay, does magnesium like to be forming cations, so positive ions, or anions, which are negative ions? So let's go to our data booklet and find magnesium. So magnesium is right here. It's in group number 2, and it likes to have a positive 2 charge. Okay, so why that's important is because, okay, now I know this likes to form a positive charge. So it's going to switch with the element here that also likes to form a positive charge. Remember, with water, you're thinking of it as hydrogen and a hydroxide. Okay, so hydrogen likes to form a positive charge. Okay, so magnesium is going to switch places with this hydrogen, and then the hydrogen is going to take up the space where magnesium used to be. Okay, that's what we're doing to predict our products. Okay, so we have magnesium hydroxide. So magnesium that like to have a 2+ charge. Hydroxide likes to have a -1 charge. If you're wondering where I'm getting the charge for hydroxide there, you can look that up in your table of polyatomic ions, and hydroxide is right here. So it's got that -1 charge right there. Okay, so 2 minus 1, obviously that's not 0, so we got to do crisscross applesauce, which means that we're going to have 2 hydroxides. So whenever you have more than one polyatomic ion, you need to put brackets around it, and then whatever your subscript needs to be. And then for our final product, that's going to be hydrogen. Okay, now remember, hydrogen is part of Hofbrinkel. So Hofbrinkel is our memory device to remember all of the diatomic elements. So hydrogen is a part of that. Let me write that out for a second here. Hofbrinkel. So if you have hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine by itself, then you need to write that there's 2 of them. Okay? And then hydrogen's going to be a gas. All right. Another kind of confirmation that we have hydrogen as a product is, like I said earlier, the question tells us hydrogen gas is being collected. Okay. Let's take care of the last state here, which is magnesium hydroxide. So we're going to have to go to our periodic table, or sorry, our data booklet, and then go to our solubility table, which is on page 6. So we've got hydroxide, and then it's saying, okay, group 1 ions or ammonium, those things with hydroxide are going to be very soluble. Okay, but anything else is going to be insoluble. So let's take a look and see, okay, is magnesium part of group 1? We know it's not ammonium. Okay, so looking here, magnesium's part of group 2. So that means it has to be insoluble when it's with hydroxide. Okay, now the reason why I'm saying it's insoluble when it's with hydroxide, let's go back, is because it's not a group 1, it's not ammonium, so it fits under most. Let's get rid of that. Alrighty, now let's make sure we balance this. So with balancing equations, it doesn't really matter where you start, but there are places to start where it's easier. So me, in my mind, I'm thinking, oh, hydroxide, there's 2 of them and it's in a compound, so it might be a little bit trickier to balance that one. Okay, hydrogen, it's by itself, and magnesium's by itself, so those are going to be easier to balance. So that's why I'm starting first with hydroxide. So we've got 2 coming out, I want 2 going in. So again, remember, I'm treating this as a hydroxide and then hydrogen for the water, just to make life easier. Okay, so there's 2 hydroxides, 2 hydrogens. Going in, we have 2 hydroxides and 2 hydrogens coming out, so that's good. We got 1 magnesium going in, 1 coming out. That's perfect, it's balanced. Okay, let's organize our information. So what volume of hydrogen gas, so volume equals, we don't know, and it's saying that the hydrogen gas is at a pressure of 94 kilopascals and a temperature of 24.5 degrees Celsius, but remember, we never use degrees Celsius, we always use Kelvin, so we're going to add 273.15. If you want to remember for converting between degrees Celsius and Kelvin, you're remember to add 273.15 versus if you were going from Kelvin to degrees Celsius, you'd have to subtract 273.15. So how I always remember that is Kelvin is going to always be the higher number compared to degrees Celsius. Okay. All right, so 24.5 plus 273.15, that's going to give us 297.65 Kelvin. Okay, what else do we have? We have with 10 grams of water. So mass of water, 10 grams. So whenever you have mass, you're going to have to figure out molar mass. Okay, so pause the video and try to figure out what molar mass of water is. And then once you're finished that, you can hit play and resume the video. Okay, so just as a quick refresher here, hydrogen, those are each going to be 1.01, and then the molar mass of oxygen is 16, so we add those all together and we get 18.02. Alrighty, so now that we have everything set up, we've finished step 1, which is balance chemical equations. Step 2, we need to find the moles of our given substance. So in this case, the substance we have the most information for is going to be water. So let's start off. So we have mass is equal to moles times molar mass. Okay, but we want to find moles. Okay, so molar mass is multiplying moles, so we got to do the opposite, which is division. Those are going to cancel out. So then we get mass divided by molar mass is equal to moles. That's going to be our formula that we use. Okay. Oh, where'd that go? Okay. So let's plug in our numbers and flip this equation around. So our mass, that was 10 grams, divided by a molar mass, which is 18.02 grams per mole. The grams are going to cancel out. And let's put that into our calculator. So 10 divided by 18.02. And we're going to get 0.5549, goes on forever. And this is moles of water, which you can write as HOH or H2O. They mean the same thing. So now that we've found our moles of our given substance, which is water, we're going to do step 3, which is use our mole ratio to convert moles of our given substance to moles of our unknown substance or our wanted substance. So I'm going to go times by fraction sign. So water is our given, and then what we want is what has a question mark underneath it. So we want hydrogen. Another way you know that hydrogen is your wanted substance is because it says what volume of hydrogen gas. So that's another clue. So the coefficient in front of hydrogen is 1, and the coefficient in front of water is 2. Okay. So then we're just dividing this by 2. So then we get 0.2774, goes on forever. And that's going to be our moles of, so water's on the top and the bottom, so they cancel out. So this is moles of hydrogen gas now. All right. So now we're trying to find volume of hydrogen gas. We already have moles, we have pressure, we have temperature, and we're looking for volume. So what formula handles moles, pressure, temperature, and volume? Well, that's going to be the ideal gas law. Okay, except for this time we're going to be looking for volume. Okay, so where do I have room here? Sure. All right, so PV is equal to nRT. We're looking for volume, so we got to get rid of pressure and bring it over to the other side. So pressure is multiplying volume right now, so we're going to do the opposite. We're going to divide by pressure. So those cancel out. Volume is equal to moles times the ideal gas constant times temperature divided by pressure. Now, let's just plug in all of our numbers here. So 0.2774, that goes on forever. It's moles. Then our ideal gas constant, which you can find on page 2 of the Nelson periodic table sheet, 314. And the units of that are going to be, I always forget them here. So let's see, kilopascal liter per mole Kelvin. Okay, temperature, what was that? That was 297. Divided by, what was our pressure? 94 kilopascals. Okay, so moles cancels out, kilopascals cancels out, and Kelvin cancel out. So our units are going to be liters, and it's going to be liters of hydrogen gas because all of these numbers, they belong to hydrogen. All right, so let's put this in our calculator. So we're going to go our answer times by 8.314 times by 297.65 equals, and then divided by 94. So we're getting 7.304, goes on forever. And that's in liters. All right, how many sig digs do we have? Looks like all of our numbers given are in 3 sig digs. So I got to make sure my answer is in 3 sig digs. So counting from the far left, 1, 2, 3, there's my cutoff line. So we have 7.30 liters of hydrogen gas.